Imagine you're cruising down the highway, your car's advanced systems quietly working in the background. Maybe your adaptive cruise control is maintaining a perfect distance, or, that emergency braking system is standing by, ready to react faster than you ever could. Modern vehicles aren't just mechanical marvels anymore. They're intricate networks of electrical and electronic systems, constantly making decisions and controlling crucial functions. But here's a crucial, almost existential question. How do we know these incredibly complex systems are truly safe? How do we build in the trust that they won't just perform their tasks, but also gracefully handle or even prevent their own malfunctions? Today on The Deep Dive, we're plunging into the world of functional safety in road vehicles. Specifically, we're opening up ISO 26262 Part 3, which focuses on the concept phase. Our mission is to unpack how safety isn't just an afterthought bolted on at the end, but meticulously engineered into these sophisticated automotive systems right from their earliest, most fundamental conceptual stages. It's about building safety from the ground up.
Exactly. And welcome back, everyone, to our series on ISO 26262. We've looked at Part 1 and Part 2 previously, and now we're diving into Part 3. This particular part, Part 3, is essentially the blueprint for safety-related electrical and electronic systems found in the cars we drive every day, well, excluding mopeds, of course. What's absolutely critical to grasp up front is its singular focus. It exclusively addresses hazards that stem from the malfunctioning behavior of these EE systems. We're not talking about a flat tire here or, a general mechanical failure. We're focused on what happens when the electronics themselves go awry. It's designed to seamlessly integrate into an organization's existing development processes, covering both the technical product safety requirements and ensuring the organizational processes are robust enough to actually deliver on that safety.
That distinction is key, isn't it? We're not analyzing how efficiently your adaptive cruise control normally keeps you a safe distance from the car ahead. We're asking, what happens when it fails to detect that car? Or when it suddenly brakes for no reason? This part of the standard makes it crystal clear. It's not about the nominal intended performance, but purely the safety aspects tied to those malfunctions. We're digging into this further. Okay, let's unpack this. Part 3 lays out what's known as the concept phase. And when we say concept, we mean the absolute beginning, the foundational bedrock for functional safety in any automotive EE system. So what are the 3 essential pillars that make up this absolutely crucial phase?
You've hit on the core of it. The concept phase comprises 3 critical sequential activities, each building on the last. First, item definition. Second, hazard analysis and risk assessment, or HARA, as it's usually called. And finally, the functional safety concept. These steps are what ensures safety is baked in from the very genesis of a product idea. Let's start at the absolute beginning with item definition. Think of this as painting a crystal clear picture of the system you're building. The main objectives are twofold. First, to clearly describe the specific system under consideration, including its functionality and all its intricate dependencies and interactions, not just with other vehicle systems, but crucially with the driver and the broader environment. And the second objective, to ensure you have a deep enough understanding of this item to genuinely support the next more complex steps, the HRA and the functional safety concept activities.
So it's about knowing your system's entire world, essentially. What it does, what environment it lives in, and crucially, who or what it interacts with.
Precisely. Clause 5, that's where item definition lives in the standard, provides the requirements for outlining everything from the system's core functionality and interfaces to its environmental operating conditions, any relevant legal and regulatory requirements, and even preliminary thoughts on potential hazards. It's truly the starting point for everything that follows. What's quite interesting is that there are no mandatory prerequisites to kick off this phase. You can literally begin with early conceptual ideas. But the standard really emphasizes the value of having further supporting information, things like existing product concepts, documentation from previous systems, or even results from early trials. It just gives you a richer canvas to work with.
So even at this super early stage, what specific aspects do engineers need to nail down about the item? Are we talking about a massive checklist?
It is comprehensive, but it's about categories of information. You need to identify things like any legal and regulatory standards it must comply with, say from UNES or other international bodies. Then its core functional behavior, which includes how it operates at the vehicle level and its expected operating modes or states. You also consider its desired performance, quality, and availability, things like expected response times or fault tolerance. You pin down constraints like its operating environment or system dependencies. And yes, even preliminary failure consequences, any known failure modes or past safety incidents that that might inform this new design. Finally, you have to understand the actuator capabilities. This means knowing the raw power your system can unleash. If your anti-lock brakes malfunction, how much braking force could they actually apply? Or how bright could a faulty headlight get? Knowing those extremes is crucial for safety planning. Here's where it gets really interesting. Defining the item's boundary isn't just about its exterior. It also includes breaking down its internal elements, its subsystems or components, and understanding its effect on vehicle, how its behavior impacts the vehicle as a whole. You also consider its function allocation, meaning how functions are distributed among systems, and critically detail operational scenarios. These are the specific situations where the item will be used: parking, highway driving, or even diagnostic codes.
Yeah.
All of this comes together to form a very clear picture of what you're building.
And the tangible output of all this foundational work in the item definition phase is the item definition document, which then feeds directly into the next stage, the hazard analysis and risk assessment.
Yeah.
Correct. It's the definitive what we're building before we even think about the risks.
Exactly. That document captures everything you've just described. It's the handover point, really.
Okay, so once we have our item meticulously defined, the next crucial step is to unveil and quantify the risks. This brings us to hazard analysis and risk assessment, or HAR, found in Clause 6. This phase sounds absolutely critical for safety. What are its main objectives?
HARO is indeed where the rubber meets the road for safety analysis. Its core aims are, fourfold. First, to identify potential hazards stemming from the item's malfunctioning behavior. Remember, that's our focus. Second, to evaluate the risk associated with each of those identified hazards. Third, to determine the automotive safety integrity level, or ASIL, for each hazardous event. And finally, to define safety goals, or SGs, that will actually prevent or mitigate these hazards. When we talk about identifying potential hazards, we're defining a hazard as a potential source of harm caused by a malfunction. To be clear, we're not talking about your car running out of gas. We're talking about, say, the adaptive cruise control suddenly slamming on the brakes when there's nothing there, or accelerating when it shouldn't be. That's the malfunctioning behavior that leads to a hazard. It's important that these are identified at both the vehicle level, think unintended acceleration or brake failure, and the more granular functional level, like an incorrect sensor input or a loss of communication. Information sources can include historical data, expert judgment, or even techniques like FMEA failure mode and effects analysis. A critical part of HARA is also defining all relevant operational situations and operating modes. You need to identify all the conditions where a hazard could occur. This encompasses diverse operational situations like urban traffic, highway driving, parking, or environmental conditions like day versus night or rainy versus snowy weather. And it also includes the item's various operating modes, whether it's active, in standby, undergoing fault diagnosis, or in a fail-safe state. The more thorough you are here, the more robust your safety analysis will be.
So we're not just looking at what could go wrong, but when and where it could go wrong. It's about building a complete picture of the danger zone. How do you then quantify that risk? I've heard about ASIL levels. How does that actually work?
Right. To quantify the risk, we use what's called the ASIL classification, determined by a combination of 3 parameters: severity, exposure, and controllability, often referred to as the SEC matrix. Severity S is the potential injury level if the hazard occurs, classified from S0, no injuries, up to S3, life-threatening or fatal. Exposure E is the likelihood of actually encountering the operational condition where the hazard could occur, ranging from E0, incredibly unlikely, to E4, high probability. And controllability C is the likelihood that a typical driver can avoid harm if the hazard occurs, ranging from C0, controllable in general, to C3, difficult or uncontrollable. The real genius of the SEC matrix isn't just a formula, it's a forced conversation, really. It makes engineers step outside the what and confront the chilling what if. How likely is someone to be in harm's way, and how little control do they have if a critical system fails? The specific combination of these SE and C values ultimately determines the ASIL level, ranging from ASIL-A up to D, with ASIL-D representing the highest level of integrity required for safety-critical functions. If a hazardous event doesn't require functional safety measures, it's classified as QM, which stands for Quality Management. And for every hazardous event classified with an ASIL greater than QM, 1 or more safety goals must be defined. These are top-level safety requirements aimed at preventing or mitigating the hazard, and they must be ASIL-rated, measurable, verifiable, and independent. The ASIL analysis must also consider various fault types, from systematic design errors to random hardware failures, single-point, multiple-point failures, even faults caused by unexpected interactions between systems. The whole spectrum, really.
So we've identified the hazards and quantified their risks with the ASIL. We know the what could go wrong and how bad it could be.
Yeah.
What's the next step in actually building safety into the system? This brings us to the functional safety concept, or FSC, covered in Clause 7. What are its key objectives?
Okay, the FSC is where you start to define the functional shield against those identified hazards. Its objectives are to specify the functional or degraded behavior required for the item to actually meet its safety goals. It defines constraints related to fault detection and control, like timing requirements and specific mechanisms. It also describes strategies for fault tolerance or mitigation, including instances where the driver or other external systems play a role. A key aspect is allocating functional safety requirements, or FSRs, to the system architecture and defining how the FSC itself will be verified and validated down the line.
So this is where we start translating those abstract safety goals into concrete actions the system needs to take.
Precisely. Let's break down the key components. First, there's the derivation of functional safety requirements, FSRs, from safety goals. Each safety goal from HARA is translated into one or more FSRs. These FSRs define what must be done functionally to fulfill the safety goal, including performance, timing, and detection constraints. Crucially, they remain technology agnostic at this stage. They don't specify hardware or software details yet. That comes later. Next is the allocation of FSRs to the item system. Each FSR must be assigned to either the item itself or to external measures, for instance, alerting the driver or relying on a mechanical fallback. They are then mapped to specific subsystems or blocks within the conceptual system architecture. The FSC also involves consideration of failures, faults, and degradation. This means defining the expected failure types, single-point, multi-point, latent faults, and critically, the system's degradation behavior. Will it shut down, reduce performance, enter a limp mode? And how does it smoothly transition to these states?
So it's not just fail safe, but fail gracefully whenever possible.
Exactly, that's a good way to put it. A core principle is the definition of safe states and of fault tolerance. A safe state is simply a system condition where hazards are no longer present or are fully controllable. The system must be able to transition to this state quickly after fault detection and, ideally, be fault tolerant, meaning it can maintain or restore safe operation if possible. This leads naturally to fault detection and handling mechanisms. The FSC specifies how faults are detected through things like sensor self-diagnostics, plausibility checks between different inputs, or watchdog monitors keeping an eye on timing. And it defines how the system responds, perhaps signaling an error to the driver, entering a degraded mode, or switching to a backup control path. The concept of functional redundancies is also outlined here. This means providing backup functional paths to maintain safety. These can be active, where both systems operate simultaneously, like having two sensors measuring the same thing, or passive, where a backup only engages when a fault is detected, such as a mechanical steering linkage taking over if electric power steering fails. This is fault tolerance. You also need to define the interfaces between the item and external systems, how it interacts with the driver and other vehicle systems like ECUs or sensors. This includes information flow, any assumptions made about those external systems, and how failures are handled at these crucial interfaces. Finally, and this is vital for audit readiness in the safety case, there must be traceability of FSRs to safety goals. Every FSR must be traceable back to its originating safety goal. Traceability isn't just a checkbox for auditors, it's your early warning system. Imagine realizing a tiny change in a software line could unknowingly violate a life-critical safety goal. Traceability is the thread that instantly tells you who, what, and where that impact happens, potentially saving millions in recalls or even lives.
So what does this all mean when we connect it to the bigger picture of ISO 26262? How does Part 3 truly fit into the larger landscape? Tying this all together.
Right. Part 3 is absolutely foundational and creates crucial interfaces to other parts of the standard. The functional safety requirements, or FSRs, that we derive in the functional safety concept in Part 3 are the direct inputs for Part 4, which deals with product development at the system level. In Part 4, those FSRs are refined into technical safety requirements, or TSRs, which get more specific about how the function will be achieved. Then those TSRs are further allocated to specific hardware and software components. This creates that vital top-down safety requirements flow. Safety goal leads to functional safety requirement, which leads to technical safety requirement, then to hardware and software design, implementation, and finally, testing. It all links together. Part 3 also has a significant connection to Part 2, which covers safety management. All the work products generated in Part 3, the item definition document, the ARA document, and the functional safety concept document, are critical pieces of evidence that contribute to the overall safety case for the product. They also provide essential inputs for the safety plan, helping to define the timing and responsibilities for all these safety activities. All that paperwork, well, it actually matters. And as we just discussed, the concept of bidirectional traceability is emphasized throughout. This means linking elements backward to their origin in HARA and item definition and forward to system design, implementation, and validation. It ensures safety completeness, allows for much easier impact analysis when requirements change, and maintains the consistency of the entire safety case. Being able to track things back and forth, that's key.
That's a lot of interconnected concepts. To make this really concrete for you listening, let's walk through a real-world example straight from the source material. The Adaptive Cruise Control, or ACC, system. Let's make this real. This is where it all comes to life.
Excellent idea. Let's use the provided sample review document to illustrate the entire concept phase process for an ACC system. First, for the item definition of the ACC system, it's described as, maintaining a safe distance from the vehicle ahead by automatically adjusting speed. Its key characteristics include several operating modes: normal, standby, a specific fault degradation mode, and a diagnostic mode. Its internal interfaces connect to things like a radar sensor and a brake controller, while external interfaces include the driver interface, the powertrain ECU, and the CAN bus communication network. Environmental conditions are also defined, like a temperature range and ingress protection rating, like IP6K9K. A crucial assumption here is that the radar sensor is cleaned periodically. Imagine the safety implications if it wasn't. That needs to be documented up front. Moving to the HARA for this ACC system, let's look at a specific identified hazardous event. The malfunction considered is failure to detect a slow vehicle ahead. Pretty serious. The resulting hazard is obviously a rear-end collision. When we apply the ASIL classification, we see a severity S of S3, meaning life-threatening injuries, an exposure E of E4, which is high likelihood on many roads, and a controllability C of C3, indicating it's difficult or uncontrollable for the driver to avoid harm, especially at speed. And bam, that combination gives you an ASIL D, the highest level of safety integrity. From this, the safety goal defined is SG01. The ACC system shall ensure timely braking or alert the driver in case of a detected obstacle. Nice and clear. Finally, for the functional safety concept for the ACC system, we can see how that safety goal translates into specific functional safety requirements. For instance, FSR01 states, the system shall detect forward obstacles within 100 milliseconds and initiate braking or driver alert, very specific timing there. And FSR02 specifies, the system shall transition to degraded mode if radar input is invalid for more than 1 second. Again, a clear time constraint. The defined safe state is to cancel ACC operation and return control to the driver via visual and audio alert. ALT detection and handling involves sensor plausibility checks and watchdog monitoring. For functional redundancy, it mentions redundancy via driver intervention alerts and fallback to mechanical brake control if needed. Interface considerations highlight that CAN message loss results in safe state activation, with the driver being notified, critical communication pathway, and the traceability is clearly noted, showing SG01 leads directly to FSR01 and FSR02. It all connects.
What stands out to you about how this example brings the whole concept phase to life? For me, it's how a seemingly simple malfunction, like failure to detect a slow vehicle, escalates into such a high ASIL, and that requires such precise functional requirements and fallback strategies. Yeah, you can really see it's not just an abstract idea, but a very tangible set of engineering challenges that engineers have to think through right at the very beginning of the design process. And there you have it. So we've covered a lot today, taking a deep dive into ISO 262622 Part 3, the concept phase. We've explored the critical steps of item definition, hazard analysis, and risk assessment, HARA, and the functional safety concept, understanding how these foundational steps ensure that safety is inherently built into complex automotive EE systems from the very beginning.
This structured, systematic approach is profoundly important. It really is fundamental. It's precisely how automotive engineers break down incredibly complex safety challenges into manageable, verifiable steps right from the initial concept of a project. It's what gives us confidence in the advanced features in our vehicles. This raises an important question, though.
As vehicles become even more autonomous, how might the definition of controllability within the ASIL classification continue to evolve? Especially as the human driver's role potentially shifts and the car takes on more and more decision-making responsibility, who or what is ultimately in control in a hazardous situation. It's a fascinating challenge for the future of functional safety, something to think about. Thank you for watching this video on Part 3. Now we will meet on Part 4. For more videos, do like, share, and subscribe to our channel. Until next time, stay curious.